let me summarize what we are. So we're talking about the Ziegler-Nichols tuning method, and that is plug and chug with that table once we find the ultimate gain and the ultimate period. The practical way of getting them is not trying to do experiments, but getting experimentally through step changes or pulse changes, GU. And once you have GU, then conceivably you could be iterating and have an iterative approach to find KU and omega C naught, which gives you P. But instead, you can avoid iterations if you reason out that if you factor out the unknown magnitude of Kc, of Ku, and to factor out the minor absolute value of Ku, I have to factor GOL as Gu prime times absolute value of Ku. So Gu prime is going to be equal to Gu if Kc is positive, which means if Gu0 is positive. On the other hand, it has to be minus Gu if that's negative. So we do a body plot of Gu prime, and then Pu is 2 pi over the crossover frequency for that plot, and the magnitude of Ku is 1 over the magnitude of Gu prime. So clear with the summary of the method? So let's do an example. So I'll tell you what, let me make one modification to the example. Did I erase it?
Yeah, you did.
I erased it. I'm good at doing things like that. All right. Yeah, I erased it to do the. There's a next door classroom has more doors. So this is the next question. Okay, so here's our example. Let me put a minus in front of what we had. Okay, what did I have, guys?
3s plus 1.
So let's make it minus 3s minus 1.
4s plus 7s plus 4. That's the best question.
Let me give you something that has Gu. So, what's the very first thing we need to do?
Stability?
Absolutely. Before you check Gu0, before you check anything else, if I'm going to use anything that involves directly or indirectly body stability criterion, you need to check that you're open loop stable.
When do you want
Any quadratic that has no change in sign is stable. Okay? Because what's the root array?
When do you want us to use the approximation? The e to the negative 8s?
Why would I ever use the approximation?
When do we use it?
Only if the poles you need to find are not a polynomial equation. Here we're talking about open loop poles. Is that polynomial equation? So if you use the root array, sorry, the Padé approximation, where you are not supposed to, you're going to lose a lot of credit, you understand that, right? You only need to use it if the characteristic equation is not polynomic. If it's polynomic, don't use it. Not to mention that you're really messing up your exam, because instead of having, for example, a nice quadratic, you use Padé, you would have now a cubic. It's factored, but my experienced students who did that then multiplied the coefficients and really had a great time.
So you only do that when you have 1 plus GUGC equals 0?
Yes. because with the e to the minus ds, if e to the minus ds is what makes it not polynomial in the 1 plus GUGC. But here, the e to the minus ds is not in the denominator. Okay?
It's not.
Felix? No, it's
Okay, got you.
the denominator is polynomial. For open loop stability, the denominator is polynomial. Only for closed loop stability, it's not polynomial. Remember, closed loop denominator is 1 plus GUGC.
You say the e to the minus ds is not in the polynomial.
It's not part of the polynomial, it's not part of the denominator.
Okay.
But in a closed loop system, where the denominator is 1 plus GUGC, 1 plus GUGC has the e to the minus ds, it's not a polynomial. That's when you need to use by the approximation. All right. So, open loop stable check. So now we proceed with figuring out what GU prime is. So, GU of 0 is what? It's negative. Therefore, GU prime will be minus GU of 0. So GU prime is going to be 3s plus 1 over 4 s squared
Put a difference on
plus 7s
these
plus
numbers
2
with
e to the
against
minus 8.
the explanation before.
Question, Felix?
Wait, do you understand?
One question?
No.
No question? No, I don't
No
know.
question.
No, no question, no question.
Andrea? I don't.
You have this negative GU of 0, but you have all the rest of it.
Wait, do you
No.
understand, do you understand when you do it and when you don't?
Mm-hmm.
Okay, alright, I just got it.
Yeah. When we do body plot of GU of S, of GU prime of S minus GU, there shouldn't have been of 0. Yes.
What?
I should have put of 0 here. It's the, when it GU prime of S is minus GU of S. Is that? We do body plot of GU prime of S, not GU prime of 0. GU prime of 0 is just a number. Doesn't depend on S equals I omega. Right? Now, body plot is what we get if we put S equals I omega. So yes. All right. Everybody clear? Megan, okay? Claudia, you okay? This time I didn't go to Megan after Megan. You're expecting that, Megan, weren't you? All right. So everybody ready? Did everybody get the class program to work? Yes? So for my students, what I found out is you need to run as administrator. All right. That time is 8. What's the degree of the denominator? 2. What's the zero for the coefficient? 2, right? 2, 7, 4. Okay. The next one is 7. The next one is 4. What's the degree of the numerator? 1. And the zeroth order is 1. And the first order is 2.
What
So
about
8, 2, the pigs are 2, 7, and 4. Degree of numerator 1, and the a's are 1 and 3, right? I did it right.
why is not -1 and negative?
Because I do the body plot of GU prime. That's the whole thing, not of GU. Because I needed to have factored out something that has 0 phase lag, 0 argument.
If I,
0, I mean, yeah, argument.
if I type here -1, can I change it just like that?
What do you mean?
Like for the coefficient?
Just delete it. Delete it.
Delete it. We don't type one. Yeah.
Everybody clear? All right. So, click to continue. Both roots here happen to be real. You can see the denominator roots. Okay. And do you want to see for a specific frequency? There are two ways you can do it. Important thing, I need to go to a high enough frequency to go past omega C naught. What happens at omega C naught? Phase lag is minus 180. If you choose a specific frequency, instead of showing minus 190, it will show plus 170. Because with a single frequency, there's no way you can figure out how many times minus 360 we subtract. So we can look at specific frequency, or we can do a beginning plot, see where we are, and replot it with different minimum and maximum frequencies. So let me just do specific frequencies. Okay. What do we know that at small enough frequencies, the phase lag should be close to 0. So if I put like 0.001, you can see the phase lag is minus 0.48. That's pretty close to 0. Minus 0.48 degrees. So let's say another one. How about 0.1? 0.1 you can see is minus 48. Let's put 0.3. Say yes, 0.3. Minus 147. I'm getting close. How about 0.5? Notice it went positive. The plus 113 that you see in reality would be minus 180, minus 67, so minus 247. So 0.5 is high enough. So we can use 0.5 as our maximum frequency, and something low like 0.01 or 0.001 is our lowest frequency. So we can say no, we don't see another frequency. Absolutely don't make the mistake to say no, because then you get it out of the program here. Say yes. Minimum frequency, what should we use? 0.01? Maximum frequency, so 0.5 will work. 1600 points. Go. Good. Here we go.
So you did 0.011 and 1600?
Say again?
0.01.5?
Yeah, I use 0.01, that's why this is minus 2 and 0.5. So I always want you in an exam to show me graphically what you're doing, and then use the table to get more accurate runs.
Do we have to send you the graph?
Not to me now, but in an exam, yes. In an exam, yes, you need to be capturing that as well. You can capture the screen.
I can't. My computer doesn't know it's a computer. Like I can't even turn up the volume, or it's retarded.
If you go to start menu, there should be something called snipping tool. Find that you should be able to use.
Okay, I do have that. Okay, got it.
Yeah.
Thanks.
Yeah. Okay, so I'm capturing the screen. Control Alt Restream. Let's start paint. MATLAB is here. Okay, so remember the procedure. You go minus 180 until you hit which curve? The brown or the other one?
The brown, yeah.
It's color coordinated, right? So careful. The brown axis has the minus 180. I should be using one for phase one class this line, both below and above. Below because that's what? That's log omega C naught right here. And above, I'll start from below. Alright, that's it. That's it. No, actually, I just need to go. Yeah. Okay, this is just to show you where omega C naught is, log omega C naught. And
Damn it.
is my closed loop system stable? Yes?
Yeah, it's negative.
So if I had found a value positive, would have been unstable?
Yeah.
You sure?
What was the question?
Is my closed loop system stable? Do I have stability?
Yes.
Yes. Sounds like a no.
This doesn't prove stability.
Say it.
It doesn't prove stability because you're plotting G prime.
Thomas hit the nail on the head. Exactly. This is not a plot of GOL. This is a plot of GU prime. That protects the stability of the closed loop system. Okay? So whether this number was negative or positive doesn't matter at all. That simply, if it's negative, that means that KU is greater than 1. If it's positive, it means KU is less than 1. That's all it means. Nothing else. Has absolutely no impact on a stability discussion. Stability, always you need to do body plot of the entire GOL. You need to have a controller transfer function. You form the GOL, which is GU times GC. The body plot of that will tell us about stability. Here we're doing body plot of GU prime. That's not GOL. It's an alternative body plot that allows us to find KU and PU without iterating. Okay? So, if that was a body plot of GOL, then we could talk about stability. Here we can. So here is, so if you put something down, so here is log omega C naught. Okay, right here. And here is what? The magnitude of GU prime at I omega C. Okay, well, hope you can, yeah, if I highlight it, you can read it. So that's the magnitude, log of the magnitude of atoms. So log of that. Correction, log of that.
Paint, you can't correct it.
Yeah, all right, well.
I have to retype it.
Yeah, but can I at least
No, you have to retype it.